Welcome to the 14th episode in the mathsonlinetuition.com videos going through the C1 book. We start off with the rest of chapter 7, so part 2 of our 2 videos going through differentiation. 7.4. You can find the gradient formula for a function such as fx equals x to the power of 3 plus x to the power of 2 minus x to the power of 1/2, where the powers of x are real numbers, as follows, and where an minus 1 all the way up to a0 are constants. You know that if y equals xn, then it's differential where y is differentiated with respect to x equals n multiplied by x to the power of n minus 1. It can be shown if y equals axn, where a is a constant, then dy over dx, or differential of y with respect to x, equals anx to the power of n take away 1. Also, if y equals fx plus minus gx, then dy dx equals the following. These standard results can be assumed without proof at A level, okay, so you don't need to worry about how to prove them. I think these are some important equations, so we're going to write them down. So we've got y equals xn, then it says that dy dx and xn minus 1. Okay, so if y equals axn, where a is constant, then dy dx equals anx to the power of n minus 1. Okay, and then finally, just to make mention of, if y equals fx plus minus gx, then the differential of y over dx minus g. Okay, sorry, that should say okay, right. So these are some very important formulas that you need to learn, you need to memorize, not the proofs, but how to carry them out. And here's some examples that we're going to do together, where it says, example 8, so let's clear this out. So let's just do the first one, A. So we have AA, we have x3 plus x squared minus minus to the half. This is A. So y equals x3 x2 minus x to the power of a half. So let's differentiate y with respect to x. We have, for the first one, plus minus x minus half. How do we do this? Let's take it slow motion using ax n minus 1. Okay, so essentially what we say here is the following. We have x to the power of 3, so this is going to give you what? 3 multiplied by 1 x 3 okay, gives us x to the power of 2, exactly what we have here. Change color up, so we have 2x sorry about that, 1, jump the gun there. So we have 1 multiplied by 2 by 2 minus 1 equals 2x1, which is what we have here, and you can work it out for the last one. Okay, and the similar thing for B and C, not difficult, and you can do it on your own. You can expand or simplify polynomial functions so that they're easier to differentiate. So in this particular subsection of 7.5, it's just instructing you that there are other means of solving equations, differentiating them when they are in particular forms. So example 9 says that you have y equals 1 over 4x, 4 multiplied by the square root of x. Remember that we mentioned before, this here is equal to 1 over 4x half. And what did we say about bringing powers from the denominator to the numerator, or otherwise the power is always negativized. So in this particular case, if we change it, if we flip it around, we'll have the quarter, but then on top we'll have to the power of minus half, x to the power of minus half. Okay, then if we differentiate this, so dy with respect to x will give us minus half multiplied by quarter x minus 3 over 2, should give you negative 1 over 8 x minus 3 over 2. Okay, and likewise for b, we'll just do b quickly while we're still here. Y equals x cubed 3x plus 1. Let's expand 3x to the power of 4 plus x 3, so 12. So dy dx equals plus 3x squared. I just want to bring your attention to something that I unintentionally done, but is a point to remember here. I don't want to confuse you, but it's very important for you to make sure that when you differentiate your d's, at least the tail, so not the tails, but the line from the d, when you say dy dx, has to be straight. Okay, dy dx. And the reason is, and this is not something you need to worry about now, that this is different to this. This is a partial differentiation. Don't worry about what that means right now, but this is a partial differentiation. And the only reason why I mention it is because I don't, when you're in the exam, or when you're writing out the different, if you're trying to insinuate that you're going to differentiate something, don't make your d's sloppy. Okay, because you know these two are contradicting one another. You want, okay, dy dx. Alright, it's very, very important. Don't give the d a curvy tail. Make sure that it is a straight line. Okay, just carrying on, we have exercise E that you can do in your own good time. You can repeat the process of differentiation to give you a second differentiation. So we know that fx equals y. Okay, this is a function with respect to x, which gives you y. And dy dx equals f dash x. So it's only suitable that d squared y dx squared equals fx. And on and on and on. You'll have d and y equals okay. It's very important for you to remember. Now if we have y equals 3x 5 plus 4x squared, then a dy dx will be 15 x to the power of 4. Remember what we said, so we bring this is equal to, okay, so we get minus 8x minus 3. Okay, then we can bring it back down. 15 x4 equals 8 x to the power of 3. We want to differentiate it again, so let's differentiate it again. So dy, so 15 by 4 gives us 60 x3, and then we have this particular one here. Remember, this is equal to minus 8 x minus 3. Let's differentiate that, plus from the two negatives 24 x minus 4, and again leaving it with all powers positive x4, and this is the answer we get here and the answer we get here. Okay, very simple, very straightforward. Examples again for you to do. And then this is just more of a read here for 7.7. You can find the rate of change of a function f at a particular point by using f dash x and substituting the value of x. So this is just something for you to read. It's just including different terminologies and different ideas to give you an appreciation of utilizing real world spaces such as spaces or actions and other kind of concepts such as volume, population, and how differentiation is vital for these particular methods. Example 12 here just incorporates what we've learned before by asking you to figure out the volume of an expanding sphere, its radius, and by the formula that you're given, and it's asking you to find the rate of change. And 7.8, you can use differentiation to find the gradient of a tangent to a curve, and you can find the equation of the tangent and the normal to the curve at a specified point. Again, this is something for you to read in your own time, and it gives you an equation of the normal at the point A is y minus f a, okay, and it's equal to this same equation here. So then you give you an example for you to run through, example 13 and 14, for you to do in your own time. And then you have some more exercises and some mixed exercises, which brings us to the end of this chapter and amalgamates all the previous ideas together and the questions that you should already appreciate. Summary of key points. Once again, we've come to the end of this chapter, and it's very important for you once again to appreciate the summary of key points. One thing I would mention at this point, now that we've come to the end of the penultimate chapter and about to start the last chapter of the C1 book, is that that you should have a folder with all the summary of key points, whether that's in a A4 folder or whether you have the summary of key points all written down in a book. It's very important for you to have, so that you can quickly go through this in your own time, whether it's before an exam or whether you're about to go into class, so that you can summarize and retrieve information. You can retract that information from a paper if you forget, or if you want to summarize and you want to utilize the ideas. So again, just some formulas, very brief sentences explaining and outlining what they represent. And again, something for you to ponder about and go over. So thank you very much for listening to another video. We hope you liked it. Please share, subscribe, and we'll see you next time. Bye bye.